This is ACM ByteCast, a podcast series from the Association for Computing Machinery, the world's largest education and scientific computing society. We talk to researchers, practitioners, and innovators who are at the intersection of computing research and practice. They share their experiences, the lessons they've learned, and their own visions for the future of computing. I am your host, Bruke Kifle. Today we're exploring the very exciting area and convergence of high-performance computing and its applications in domains like climate modeling, quantum physics simulation, and large-scale AI training, where breakthroughs in supercomputer architecture, programming, and algorithms are powering the next generation of scientific discovery and artificial intelligence. Our next guest is Professor Torsten Hoefler, Director of the Scalable Parallel Computing Lab at ETH Zurich, and Chief Architect for AI and Machine Learning at CSCS, Switzerland's National Supercomputing Centre. This year, he received the ACM Prize in Computing, one of the field's highest honors for his foundational contributions to both high-performance computing and the ongoing AI revolution. Professor Torsten's work spans MPI standards, advanced parallelism techniques, and the design of networks that power modern supercomputers, delivering orders of magnitude speedups for large-scale AI and scientific workloads. He's a Fellow of ACM and IEEE, a Gordon Bell Prize winner, and a leader in making performance benchmarking more rigorous and reproducible. Professor Torsten, welcome to ACM ByteCast.
Thank you very much, Bruke.
You have such an amazing career journey and, of course, very impressive contributions to the field. Can you tell us about your personal journey into the field of computing and maybe specifically high-performance computing, maybe some key inflection points over the course of your life that really drew you into this area?
Well, that could be an arbitrarily long story, but let me try to make it reasonably short. So actually, I was always interested in mathematics. And then it turns out that my performance for solving mathematical equations was very limited. I realized early on that with the help of computers, we could actually do better in that sense. So I could use computers as my own accelerators in the sense that we already know that they solve all kinds of simple equations. Let me add two 64-bit floating point numbers. Computers is thousands of times faster than I am very quickly. And so when I was younger, I was getting very fascinated by using multiple computers to solve a task. So for example, in my teenage years, I started building a cluster under my bed where my mother was not super excited about it, but I was more excited. And the cluster was built out of old machines, like literally 486 machines. That was a long time ago, that my school was throwing away at the time. I used a software called MOSIX to put them together into a single operating system image, essentially, such that I could run an application distributed over these 8 nodes that were sitting under my bed. So that was kind of the start of my distributed memory career in some sense, a distributed node connecting career. Well, and then I went through the normal process in some sense going forward, and I studied computer science. I actually wanted to study chemistry, and then I wanted to study physics. And then I realized that what's unifying both chemistry and physics is actually the use of mathematical models, the use of simulations, at least at the university I was. And then I thought, hey, you may want to get to the root of this, because if you understand the root, you can later easily understand the application of it. So I thought I should go to computer science as a foundation for modern science at the time. That's when I started my career in the ACM field, so to say. And then I went on to my master's thesis, and my master's thesis was in a group actually building computers, like larger clusters. The group I was at was actually building one of the first commodity off-the-shelf cluster systems in a university called Chemnitz. So it's quite small. I believe we did have the first system that was made out of like standard MIDI cases on IKEA racks, connecting hundreds of those into a supercomputer. So that was quite innovative at the time. Now I ended up helping to build some of the largest machines on the planet. So that's quite cool.
Wow, that's super, super exciting. And I think the origin story dating back to your time as a kid, I think is certainly one that's quite exciting. As you think about, I love how you captured this idea of, your initial interest being in chemistry and physics, but coming to this understanding of, the foundation of modern science really boiling down to solving material or mathematical problems. As you forayed, after your master's and maybe into your PhD and some of your early work, what problem or what set of problems were you really trying to solve early on that you think shaped the rest of your work in this field?
Oh, that's interesting. Yeah, that's a nice question. So I was starting looking at something that unfortunately turned out to be quite useless at the end. So specifically, my master's thesis was inventing a new MPI barrier algorithm. So as I mentioned, I was in that group that built that supercomputer, and they found that specifically MPI barrier is very slow in that machine, and we should optimize it. So I spent 6 months optimizing a barrier algorithm. I believe that I still hold the record for the best MPI barrier algorithm on InfiniBand, because that was the interconnect at the time. It was also quite modern. It was great. I had a great time, only to find out after I graduated, when I talked to some real scientists, that you wouldn't actually use barrier. So I optimized something that a very small number of people, like, it's not zero, but it's close to zero, actually cared about. But that taught me how to build high performance networking systems, how to build collective operations on those systems, so group communication operations, how to build MPI systems. And from there on, I was able to broaden up and actually do things that mattered later. But it's quite funny that barrier is a nearly useless operation in practice. So if you catch yourself using MPI barrier in your application, you should double check if you really need it.
Very interesting. That's certainly a topic that I'd love to revisit later in this conversation. Less so the MPI barriers and more, how we ensure that some of our work in the field of research is practical. But before we get into that, I think we've definitely used a couple key terms that I think are certainly uttered in the computing industry, but I'm sure might be unclear to many. And so for those who are less familiar, high performance computing often runs very quietly in the background, but it powers some of the most, important advances in science and technology. And this could not be more true than it's ever been today. So how would you explain what HPC is and why it's so essential today, particularly in some of the areas that you're looking at around climate modeling and AI?
That's also a longer story, so let me try to make it short. So HPC, high performance computing, is the field of computing where you require high performance, as the name suggests. And then there is a subfield of HPC that is called supercomputing. And these are then essentially the fastest computers we have on the planet. These are two different entities. Many equate them, but I would say it's different because HPC is broader. Like, HPC is really anything that requires high performance. As I mentioned, when I was a young student, more than 20 years ago, oh my God, you could already see it, that all these domain scientists, they were relying less and less on experimentation, on real experimentation. They were going more and more on simulation-based experimentation. So they had a model of their chemistry process or their physics device, and then they would simulate it in a computer to accelerate the experimental process. So basically, the idea there was just to accelerate. You could evaluate tens of thousands of material combinations, and you wouldn't need to mix them in physical form. But then you take the top 10 and you mix those only. So that was called material screening, for example, at the time. So that was computer driven. And since then, the last 20 years, this has just intensified. So the field of computing has actually taken over pretty much all modern sciences. So if you go to most modern scientists today and ask them what their major tool is to make progress in their science, they will tell you simulation and modeling. Many will tell you. You can see this at several big prizes, like Nobel Prizes, being awarded in the field of computing very recently, actually, to computer scientists. There was this running joke that the only guarantee you would get as a computer scientist is that you would never get a Nobel Prize, because there was no Nobel Prize in computer science. But now there's a new running joke, and the new running joke goes like, well, when is the time when computer scientists will get all Nobel Prizes? Because essentially 2 Nobel Prizes last year went to computer scientists, which is very shocking. But it's not shocking in the sense that it's unexpected, because, as I mentioned, more and more sciences rely on computing as their foundation. And so now, if you think this further, high performance computing is enabling these sciences to move faster. Right? Because high performance computing, all we do is we create cheaper, faster computing systems to solve very large scale problems, like simulations of proteins, new medication, planes, ships. simulation of the atmosphere, simulation of the weather, and training models like ChatGPT, driving AI. These are all high-performance computing tasks. And the community of high-performance computing makes this faster. And that means, let's say we accelerate the speed of those computers by a factor of 2, or we reduce the cost by a factor of 2. It doesn't matter. It's pretty much equivalent because we're mostly cost-bound. Then we directly accelerate human progress by a factor of 2, if you think about it. If you believe that human progress is driven by science and engineering. Right? So that's an interesting observation to some extent that many people made recently. And then the field of high-performance computing became suddenly very important, like in the public. Everybody talks about supercomputers today. Like big companies. Microsoft was one of the first companies talking about, we are building a supercomputer. Meta builds supercomputers now. Meta, a company that runs social networking. Tesla, a car company, builds supercomputers now. Google, an advertisement company, a search company, builds supercomputers now. It's every big tech company builds supercomputers. Countries build supercomputers. It is exploding the field, and it's all about solving big problems faster. All these companies build supercomputers because they want to accelerate AI methods, but AI for science is going to be the next big step. I believe accelerating sciences with these AI and computing techniques, like we've been doing traditionally with high performance computing. Does that make sense as a general overview?
It makes a lot of sense, and I think you talk about direct, tangible, practical impact, right? Being able to accelerate computing by 2x, translating to a 2x, improvement in society and humanity's progress, I think is quite exciting. But when you talk about building supercomputers, obviously you've been instrumental in designing systems like Blue Waters and now ALPS. What exactly does it take to design a supercomputer that's truly optimized end to end? And of course, I know we're time bound, and obviously I don't expect you to get into the full details, but is it a hardware problem? Is this a software problem? Is this a hybrid? What are some of the key critical components of actually designing a supercomputer that brings the benefits that you've described?
Unfortunately, it's all of the above, and it's hard to compress, but I'll do my best. So I'll address each of those a little bit. So first of all, it is a hardware problem. These supercomputers are rather large, physically large, and actually they're comparable in size to these big mega data centers that you can see from a satellite. So some of them form really physically large footprint facilities. Like the ALPS computer and the Blue Waters machine, they fit in a single building. It's a couple of 100 square meters. It's not super big, but the larger industry machines, they can get very, very big. But now what makes a supercomputer? It is a collection of servers. So it's literally take your standard server, but make it a high performance server. So buy an expensive GPU, essentially, a very high performance GPU, and buy an expensive CPU with expensive memory or high performance memory. It doesn't necessarily have to be expensive, but they often tend to be somewhat pricey. And then you put them into a single machine. Then you replicate this machine, let's say 10,000 times, because one of those machines is not a supercomputer, it's not fast enough, it's not a high performance machine. So you replicate it 10,000 times, so you buy 10,000 of those. And then what you have to do is you have to now figure out how to connect those machines to solve a single problem. So you connect them with a network, but it's not the network that we are talking over right now or the internet. It is a network that is actually significantly faster. So in some sense, many of these supercomputer networks that we run today, they have more throughput in a single room than the whole internet combined has on the planet. They can transport more bytes per second, like we're at the ByteCast here. They can cast more bytes per second than the entire internet can, but they're concentrated in a single room. So they have extremely fast communication. And that's then a supercomputer. So there are many, many details that we can talk about, like how the topology of the connection looks like, what's the technology, is it Ethernet, is it InfiniBand, and yada, yada. But at the high level, that's a supercomputer. And these accelerators that we are talking about, many people talk about these GPUs, general purpose GPUs, a very funny acronym because GPU means graphics processing unit, and then you make it a general purpose graphics processing unit. That makes little sense, but the idea is basically to say that it used to be a GPU and now it's a more general purpose accelerator. These things, they drive modern workloads like modern computational science as well as modern AI. And the network connects those together. So the CPU plays a minor role actually today in these supercomputers. It's mostly we call this accelerated computing. So that's the hardware. Now that you have the hardware, what is at least as important is you need to program that machine. And now you need a programming system that allows you to program 10,000 computers to solve a single problem, or even more, 100,000 computers. Actually, we scale up to 1 million. So we have 1 million endpoints. And that is then where MPI comes in, the message passing interface. Here, this is a programming abstraction where we program these 10,000 computers like they were individuals connected via a messaging system where you can send a message and receive a message and do these collective operations that I mentioned. And that allows the programmer to orchestrate an overall performance system that works on a single task, like training ChatGPT, for example. And then you need algorithms on top of this, distributed algorithms, parallel algorithms that enable you to use this programming system that are then encoded in this programming system, which eventually executes on the hardware. So these are the 3 levels: hardware, middleware programming, and the algorithmic level. I somehow started working on all of those because performance, if you mess up any of those 3 levels, your performance will be bad. So you have to have a holistic view. You cannot say, oh, I'm provably performant on level 2. I provably have good hardware. No, if you run a bad algorithm on good hardware, you're still bad. So it's not modular. You cannot modularize performance. You can modularize correctness, for example. You can modularize security, but you cannot modularize performance, which is a little bit annoying, but that's how high performance computing goes.
And as you maybe think about, that's extremely helpful and I think provides a really good overview. As you think about the biggest opportunities for further accelerating performance of these supercomputers, where is the biggest opportunity? Is it at the hardware layer? Is this a middleware software layer? Where are the biggest advancements that we've seen maybe in the past 5 or so years? And where do you think we'll see some of the biggest advancements in the coming few years?
We have actually seen, I mean, if we go to the recent past, has mostly focused on AI models. This is overshadowing everything. I mean, NVIDIA being the biggest company in the world in terms of market capitalization with a growth that is unprecedented of any company. And all they make is compute accelerators, right? So, but they work on the full stack. I mean, Jensen Huang often says that the company is actually not a hardware company, it's a software company because they work at the full stack. Let me just highlight changes and revolutions at each of those 3 layers. So the first layer, at the hardware layer, we have really we went from normal CPU-based compute to accelerated compute in the last 5 years, very massively. Today, more than 99% of the operational capability of a single node, or actually of the full supercomputer, comes from accelerators, comes from GPUs and not CPUs anymore. Well, maybe 95% in some cases, but many systems it's actually exceeding 99%. So that is astonishing. We switched very much to accelerated compute. Then at the middleware layer, we adopted new programming models to enable this revolution to be more open. For example, deep learning training was driven by Python frameworks. The most famous one these days is PyTorch. And then all these parallelisms, FSDP, tensor parallelism, or I call it operator parallelism very often, and all these like sequence parallelism, there are about 6-7 different forms of parallelism that are all implemented in PyTorch. So that wasn't there. Well, that was very small 5 years ago, but now it's dominating the market. So it was an extremely important revolution as well, together with Nickel, the collective communication library, or the CCLs in general. And then at the algorithm level, there were so many breakthroughs that I don't even want to start enumerating them, because we started from transformers a long time ago, but we basically went to all kinds of different innovations on these transformers. And one very well-known innovation that actually disrupted the stock market quite a bit was DeepSeek, as we've seen at the beginning of the year. What was it, $500 billion or up to $1 trillion, depending on how you count, loss in US stock values. But this was mainly an exercise in optimization. If you actually read what the Chinese colleagues did, they used FP8, invented the technique multi-head latent attention, or used the technique multi-head latent attention, which is an optimization of KV mechanisms. And they have done a couple of more optimizations, mainly on the communication side. And that was just great. Right? And they used MOE very effectively, but that also existed before. At all these levels, you need to innovate to make a difference. That's what I meant. It's not, you cannot make it modular. You have to see the holistic view across the whole stack. And each of those enables breakthroughs that were unthinkable years before the breakthrough happened. And I believe in the future, this will continue. I have a hard time predicting what exactly will happen in the future, but I'm very, very optimistic that we will have several breakthroughs at all of these variants.
Super, super insightful. I think that's quite exciting.
ACM ByteCast is available on Apple Podcasts, Google Podcasts, Podbean, Spotify, Stitcher, and TuneIn. If you're enjoying this episode, please subscribe and leave us a review on your favorite platform.
We touched on a couple interesting things on the hardware side. You covered MPI. One of your key contributions has also been in actually, as we talk about AI, popularizing 3D parallelism for actually training these AI models. Can you maybe help us understand what that means and why it's so effective?
Yeah, that was very simple, very interesting. Well, in some sense, that happened very early on. That was 2017, 18, end of 2017, actually. And when you look at these models, that at the time, most people were using simple data parallelism. So how does data parallelism work? You would replicate your model to, let's again work with these 10,000 accelerators, right? You would replicate your model essentially 10,000 times. And then you would run different data through each of your replicas of the model. And then each of these replicas would learn from the data. And what you would do is you would essentially globally average either the gradients, the update to the weights, or the weights themselves. And that's now a technical detail. And then each of these models would be updated after that operation. So that's great. That's a very, very effective, very cheap method to implement. This is what everybody used. But what happened then in about 2017? And so various companies, I was at the time, actually slightly later, at a sabbatical at Microsoft, helping them to build lots of infrastructure that you can now guess what that did in the OpenAI collaboration. But the idea was that we couldn't store a model anymore on a single accelerator because the model got too big. Like at the time, the models were getting bigger and bigger and bigger, and they simply exceeded in size the memory capacity of an accelerator. Well, that's bad. So if you don't fit your model, you couldn't replicate it. So now we would have to replicate the model across multiple accelerators. And the first option is, well, each of those models consists of multiple layers. That's a very simple observation. So you could now put the first half of the layers on accelerator 1 and the next half of the layers on accelerator 2. Okay? That is called pipeline parallelism. You quickly realize during training that is actually complicated because you would have to go backwards during the so-called backward pass and update the weights with the previously stored activations. So that's again a technical detail. So you have a forward and a backward pipeline. I don't want to go into too much detail. You can watch lots of talks that I have on YouTube online that explain that. But that is one dimension, so to say. You have one dimension that is the model replicas. Let's say this is the vertical dimension. And then we have the horizontal dimension, where we now cut each replica into multiple pieces. Now, if you have 10 replicas, and you cut each replica into 10 pieces, so each piece has 1/10 of the layers, then you already employ 100 accelerators, 10 times 10. Right? That's 2D parallelism. What we realized then very quickly in many internal projects, which we didn't publish at the time, but it doesn't matter, realized, well, if you actually do this, your training would simply be slower because for each replica, you would need to go through multiple layers. And if each set of layers is on a different accelerator, you would now not make the whole thing faster, you would actually make it slightly slower in terms of latency. You would make it faster in terms of throughput because you can pipeline it. Like while the first accelerator is idle, it can already process the next data point while the second accelerator processes the first data point. So it's really like pipelining. So that gets you higher throughput, but also higher latency. So now the question is, how do I get the latency down? Well, I actually get it down if I now parallelize each of these layers. So remember, we have 10 model replicas. Each of these 10 model replicas is distributed to 10 different machines, layer-wise. And now on each of those 10 machines, we cut it again in 10, but we now parallelize each layer. And that is often called tensor parallelism or operator parallelism. That now allows us to be faster again, because if I solve each layer with 10 accelerators, this could, in theory, be 10 times as fast. In practice, it's usually slower because of Amdahl's law and all kinds of overheads. But that would give you the third dimension. And then you would have 10 times 10 is 100 times 10 is 1,000 accelerators employed in a logical three-dimensional communication pattern. Because you only communicate with your neighbors in each dimension. That is quite nice for designing systems, that insight. And that's what many people called a three-dimensional parallelism. Today, it's actually somewhat outdated because today there are more dimensions that people added. So today we are talking about 4- or 5-dimensional parallelism. Actually, I know a total of 6, but some people argue the 6th one. So you can extend this model into more dimensions. And that was the basic idea of how to parallelize deep learning workloads or distribute them and parallelize them.
As we think about the benefits of this, obviously, you're accelerating performance. Is there cost benefits? Is this more energy efficient? What drives all these large organizations to actually pursue these advancements? And as you think about the real world implications beyond just scaling up performance of compute, are there other side benefits of these advancements as well?
Well, it's partially a performance benefit. Yeah, it is a performance benefit, but it's often not a cost benefit. What you gain from parallelizing is capability. So as I mentioned, the model would simply not fit on a single accelerator. So you must parallelize it to have a larger model. And the major progress in recent years in AI came from larger models. There's this very famous Kaplan et al. Paper from OpenAI on the scaling laws of models. And that basically says, as you increase your model size, you will get more and more capability. So that was the hope at the time. We now know it's true to some extent. And so we needed to go parallel to enable larger models. That was the first one. So it's an opportunity that it enables. It's an experiment that we were able to run, or many were able to run. And so that was important. And then secondary was, of course, after you have enabled that capability, you needed to get that capability as fast as you can. Because what you also know is that there's competition in the field. You basically want to be faster than your competition. And then you use high performance computing, now that you can load and train the large model, to make the training as fast as you can, that it only takes you 2 months and not 10 years. These are actually realistic numbers. So typically it takes about 2 months, but without many optimizations, it would easily take you 10 years. And of course, in 10 years, you'll be retired also. I'll be retired. and so it doesn't change. So you also need to make this progress at a certain rate. And very often, both of those come at the cost of cost. Like the more you parallelize, usually the more expensive it goes. So you have to find an interesting sweet spot. By parallelization, you will very rarely save cost. You will improve performance.
Yeah.
And you will improve capability, but then it usually costs you more. But the nice thing is, even in theory, you can very often prove that your cost is a logarithmic multiplier. It's not linearly worse.
Super interesting. Okay. Very, very insightful. I think, you mentioned in some ways how this is a core breakthrough out of necessity, right? To be able to support these large scale models, we had to make advancements in how we think about, the 3D parallelism. Can you maybe share a story where your research in system design has really enabled a very interesting scientific or AI breakthrough?
A specific story. I mean, yes. So we had this. That's now on the modeling side. And about the AI things, there are many NDAs that I have to be careful with. On the scientific modeling side, we actually were partnering with a wonderful team at ETH Zurich, simulating heat dissipation in transistors. The whole field of computing is driven essentially by Moore's law, or has been driven the last 40 years by Moore's law, which roughly says that every 18 months, the number of transistors that you have at your disposal somewhat doubles, and everything else is constant. Like the cost is constant, the energy consumption is constant. I mean, if you assume the large scaling as well. And so basically you get a free doubling every 18 months. Right? So the 18 months has shifted. So it's now getting longer. This was due to the fact that elements got smaller and smaller and smaller. And on the transistor side, what happened then is they got so small that now quantum effects play a role. As you know, a transistor works by changing from leaving electrons through to not leaving electrons through, like 0 or 1 state. Either a high resistance or low resistance based on the electrical signals on one of the contacts. So now, even if it's supposed to be closed, unfortunately, some electrons tunnel through. That is called the leakage energy, and that is a huge problem. Because they don't really close that well if they get very small, because electrons tunnel through. And so we worked together with a scientist, Mathieu Louisier, and his team, who is an expert in simulating these effects, to simulate a realistic size set of transistors in order to build better transistors in the future. Because these transistors, you can now imagine, you can build them in different shapes. And these shapes have very interesting trade-offs about the loss energy, the functionality of the transistor, so how many electrons you need to actually close the gate and to open the gate. So that's your power consumption, right? It gets quite complex in the details, and I don't want to go into too much of the details. You can read this yourself. And so what we help there is make this application enable the largest transistor run that we have ever been able to do, or scientists worldwide have ever been able to do, and improve the performance of this run by about 100 times, 98 something times. And so that was a breakthrough that enabled many manufacturers of transistors to build better designs, to simulate better designs for their transistors. That was 2019. That's when we got the Gordon Bell Award for this, which is one of the high awards in the field. Yes, that was a breakthrough that we enabled. I always joke and say, well, we use transistors to make better transistors in the future. And much of that credit, of course, goes to Mathieu Louisier, who's the actual scientist. I have only dangerous half knowledge in how transistors actually work. He knows that for sure. But my team contributed the performance optimization, which partially enabled that breakthrough. It's always two things, right? You need the science case and you need the performance to enable the science case. So it's really beneficial to work together with scientists in our field.
Interesting. Okay. Super, super insightful. And maybe as you look ahead, what do you believe will be some of the most important shifts or innovations in HPC and scalable parallel computing that will redefine how we solve complex scientific problems, such as the ones that you cited, but also real world problems in AI? Or perhaps how do you think about some of the foundational assumptions of HPC that perhaps we need to rethink as we think about solving the next sort of wave of scientific and real world problems?
In HPC, the field has been for a very long time driven by computational science. Literally, these big computers, since I can think, were built to solve big modeling and simulation problems. And only recently, 2019 it started, that this all switched to AI. Right? AI as a workload on high performance computing systems did not really exist in a significant manner before 2019, let's say. Maybe 18, I don't want to say the exact number, but recently. And so they were all designed to solve these high performance computing problems, and that was great. And one of the differentiating factors, what you needed to solve these modeling and simulation problems, for example, if you want to predict the climate on Earth in 30 years, you would need a floating point precision 64-bit, FP64. Now, with the new revolution of AI, we realize that actually for AI systems, you don't need that much precision. Because interestingly, if you look at biological neural systems, like my brain, for example, my brain can differentiate something in the 20s at different voltage levels. And if you think about this, something in the 20s voltage levels is 4.6 bits of precision. So my brain runs at less than 5-bit precision. So why would we run AI models at 64-bit precision? Of course, we don't. As I mentioned earlier, DeepSeek pioneered the use of 8-bit in training. So we are now using 8-bit precision in many training and inference systems. Many still use 16, but I think we're going to 8-bit. So that's now a problem for traditional HPC because the AI field is 95% of the revenue of NVIDIA and other companies who make hardware. So they will naturally focus on where the money is. So they will naturally focus on low precision computations. And HPC needs high precision computation. So I think what we need to invent at this point is how do we deal with that in the modeling and simulation field. And I have to be careful. I made a mistake. I shouldn't have said HPC needs this because AI is a field in HPC. Modeling and simulation needs this. So I think we really need to innovate to not leave the scientific simulations behind. But then the other opportunity is, and this is very important, and this is going to launch a whole lot of different works. I mean, in my group, I'm working on this. Many people work on this. Jack Donguera works on this, and he leads that field of mixed precision. So that's already well ongoing. A much bigger possibility I'm actually seeing to revolutionize modeling and simulation is the use of AI techniques themselves. So AI for science. But that is very dangerous. You have to be very careful. Like, you can easily get fooled because these AI models, they always learn how to cheat really well. So they take all the information you give them in kind of weird ways to make their predictions. And sometimes you can catch them cheating. Like, for example, if you're fascinated about a climate model that runs for a very long time, stable, you may realize later that, well, if you feed the date of the prediction into the model, it may just not predict the future, but actually predict the most likely weather on the 15th of January consistently for the next 100 years. That is not a useful prediction because it does not take into account how the CO2 concentration changed in the atmosphere in 100 years, whatever you want to predict, if you just get a likely sample for 5th of January. So that's something very dangerous. And so physics-based simulations do not have that problem because they often work by first principles. You can prove that your prediction will have certain properties, while in AI models, you typically can't prove. And so that's a challenge. Like, you need to figure out how to use these data-driven methods to reliably predict physical simulations of physical processes. And that's going to be super exciting as well. I'm mega hyped about this. There are many, many approaches today, physics-informed neural networks and many data-driven approaches, but I think there's a lot to be done. And then the third one, which is in some sense the most meaningful one, but also the most, the biggest one in some sense, is can we use LLMs and these artificial intelligence, these reasoning models that we have right now, to turn into scientists? So can they replace our reasoning, proving, hypothesizing process? And I strongly believe they can at least amend it and help us in interesting ways. So I always like to talk about constructive hallucination in that context. Because if I explain myself as a scientist, what I do, I make an educated guess. And I call this a hypothesis. And then this educated guess, I go and prove it. And once I have proven it, I have extended the knowledge that we have as humans. But it started from the educated guess. Because if I wouldn't have guessed, I would have not been able to come up with a hypothesis, a research hypothesis, and I wouldn't be able to prove it. So many models can actually do this educated guessing as a form of constructive hallucination. You could train a model to make an educated guess because they have a lot of knowledge. It's well into the interpolation space, so it's well in their knowledge database to make this guess, and then we just need to convince them to prove it. So that's a big part of the scientific process. And so we're doing a lot of research in this area using reasoning models to help with that process, to amend scientists. So in some sense, this is then, if you manage to do this, these models can invent simulations. They can do anything that humans have invented to some extent in the past. Then it gets interesting. And so I think of these three tiers: moving scientific simulation forward through using AI techniques, replacing parts of scientific simulations with AI and data-driven techniques, and then enabling AI to do all of the above.
Super, super insightful. Yeah, I think it certainly speaks to the important role that the technologies that supercomputers and high-performance computing is enabling will also have reverse effects on the field itself. So I think that's quite exciting. Your work, and you had touched on it earlier, going back to your early days and some of your contributions with MPI barrier. You talked about this idea of doing work that has reach into the real world and practical impact. And so with your long-spanning career and some of your contributions, not just in academic research, but in actual building of infrastructure and real-world impact that has enabled very, very tangible, use cases, how do you generally think about bridging theory and practice in your work? And perhaps what advice would you have for younger researchers entering this space?
That's a great question. So I have learned over time. So I'm sitting in a weird spot because, as I mentioned, I started with mathematics. I'm kind of a hobby mathematician. But then I realized that it's much more fun for me to build systems that actually work and make a difference. So somehow I'm an engineer now. But I'm an engineer who really appreciates math and models, trying to develop deep understanding. By the way, in my understanding, mathematics is nothing but a simplification of the world with models that enable us to think much cleaner and clearer about what the world does. So many people think math is complicated, but it's actually a simplification of what's going on in engineering. So I'm an engineer. And then as an engineer, you have to be very careful that you engineer systems that are actually useful. And I learned later in my career, not as a student and maybe a little bit late, that it's very important to stay connected to the real world. And so this is when I started spending time in industry myself. I would give this as a recommendation to many. I would not do it too early, because the problem is, of course, by definition, industry, they have to generate revenue for their stakeholders. So by definition, at industry, what you have to do is you have to support the mission of the company you're at. By definition, in academia, what you do is you first of all, while you're in your educational process, you build your own knowledge. You educate yourself, mostly a selfish process. While you're learning, you're ingesting all that knowledge to later be a better industry player in some sense, or be an academic. And now the question is, when you make this decision, do I want to go to industry or to academia? You have to be very conscious about this. Because during your studies, you're funded by society, either your parents early on or later with stipends or whatnot. You're funded by society to improve yourself. But then when you make the decision to continue in academia and to educate other people and build open sky research, or to go to industry, you have to be very conscious, because when you go to industry, typically, as I mentioned, you're there to generate a profit for the stakeholders, including yourself. In academia, what you're doing is you're helping other people to be educated and not necessarily generating a profit. So now I wouldn't say that one of them is perfect or the other. I'm not even clear. I like a combination of both, because in order to generate profit, you need to do something that's societally relevant. In academia, you can very easily get lost and do something that's not relevant for anybody, but it's fun. Right? This is very easy. And so now I think there's a very fine line that I myself chose to work on in between academia and industry. So basically what I always do is I go to industry and watch them solve real world problems and pick the hardest problems out of there, and then move them into an academic context to solve them. And then when they're solved, I try to bring them back to benefit society. It's an interesting mix of the two, and I would recommend everybody should or could find that mix. It really depends on the person. I mean, I know many people who are perfectly happy developing theorems all day long that may or may not be relevant. And many of those turn out to be extremely relevant later. But at the moment they develop them, they may not be relevant. But then later, 50 years later, they get the Turing Award for it. So this is always possible, absolutely. And when there are people who are more happy on an immediate feedback, like myself, where I'm seeing, okay, I architected that system. That's one of the largest systems on the planet. That is great, and I can be proud of it. So it really depends on what you want to achieve and what you want to get as feedback from society.
I think that's extremely, extremely valuable bites of advice. For one, it's certainly a personal journey, and the kind of gratification that you seek in the real world impact of your scientific contributions may vary person to person. But I think great pieces of advice on, staying close to industry, perhaps not too early in your career, but at some point. And I think your, approach of identifying the most compelling or hardest problems, bringing them back to an academic sort of research environment, achieving those breakthroughs, and then ensuring that they are able to see real world impact by, hopefully bridging that research to practice, I think extremely, extremely valuable. So I think that leaves us with really, really valuable takeaways for our listeners and a great point for us to wrap up on. And I think through this conversation, certainly we've uncovered that, high performance computing isn't really just about speed, though while that is one aspect, it's really about unlocking, entirely new possibilities in science and in society. And so as systems grow more complex and more impactful, especially work like yours, Professor Torsten, will ensure that they stay fast, efficient, and trustworthy. And so thank you for your work, and thank you for joining us on ByteCast.
Thank you very much for inviting me, Bruke. It was fun.
ACM ByteCast is a production of the Association for Computing Machinery's Practitioner Board. To learn more about ACM and its activities, visit acm.org. For more information about this and other episodes, please visit our website at learning.acm.org/BYTECAST. That's learning.acm.org/ByteCast.